Welcome to the second lab session of Lab 2 User Programs. So, as you already know, an objective of Lab 2 is executing a user program in Pintos. So, in the last session, we have learned two topics, parameter passing and system call infrastructure. And in this session, we will deal with file manipulation and inter-process communication. This slide shows file descriptor in Unix. Unix-like system accesses to file by using file descriptor. In Unix-like system, each process has a file descriptor table, and file descriptor table is an array of pointer, and each pointer is pointing to a file object. There are various kinds of file objects in Unix. For example, keyboard file object, monitor file object, and I/O file object. So what you have to do is implementing file descriptor table. So each process has its own file descriptor table, and the maximum size of file descriptor table is 64 entry. File descriptor table is an array of pointer to structure file, and FD, which is file descriptor, is index of file descriptor table, and it is allocated sequentially. So note that file descriptor 0 and 1 are allocated for standard in and standard out respectively. So open function should return file descriptor, and close function sets 0 at file descriptor entry at index FD. First thing you need to do is allocating file descriptor table. Please define FTT, the file descriptor table, as a part of thread structure, and allocate FTT at kernel memory area and add the associated pointer to add thread structure. So here are a few tips to implement file descriptor table. First, when the thread is created, please make sure to allocate file descriptor table, initialize pointer to file descriptor table, and reserve file descriptor 0 and 1 for standard in and standard out. Second, when the thread is terminated, make sure to close all files in the file descriptor table and deallocate the file descriptor table to prevent memory leak. And you may need to use global lock to avoid race condition on file. So you can define a global lock on system call.h and initialize the lock on system call init. And make sure to protect file system related code by using global lock. You also need to modify page fault function to pass the test. Some Pintos tests check whether your kernel handles the batch process properly. Pintos needs to kill the process and print the thread name and the exit status -1 when the page fault occurs. So we have to modify page fault function to satisfy these test requirements. So you have to implement file-related system calls. This slide shows a set of system calls you have to implement. First, create system call creates file which has the size of initial size. You may need to use file_sys_create function to implement this system call. And this system call returns true if it succeeds or false if it fails. You also need to implement remove function. This function removes file named file, and you may need to use file_sys_remove function to implement this system call. And this system call returns true if it succeeds or false if it fails. And this system call should remove file regardless of whether the file is open or closed. And you also need to implement open system call. This system call opens the file named file and returns its file descriptor. And you may need to use file_sys_open function to implement this system call. Open or close? open or open. Open. 이거? And write system call writes size bytes from buffer to open the file FD. This system call returns the number of bytes actually written. If the FD is 1, this system call writes to the console using putBuf, otherwise write to the file using filewrite function. And 6 system call changes the next byte to be read or written in openFile FD to position. You may need to use file6 function to implement this 6 system call. Tell system call returns the position of next byte to be read or written in openFile FD, and you may need to use fileTell function to implement this system call. And close system call closes file that has the file descriptor FD, and you may need to use fileClose function to implement this system call. And what you have to consider is denying rights to executable. So please prevent the OS from executing the file that is being modified. You should not allow the file to be modified when the file is open for execution. So when the file is loaded for execution, please call file deny write, and when the file finish execution, please call file allow write function. So in load function, where the file is loaded for execution, please call file deny write function when the program file is opened. And in process exit function, where the file finish execution, please modify the current process to close the running file. And what we have learned so far is the existing Pintos task. So to check whether you have done well or not, we can use makeGrade command. From now on, we will deal with additional tasks for extra credit. So we're going to deal with inter-process communication. So the main goal of inter-process communication is implementing pipe system call. To implement pipe system call, you have to allocate a ring buffer in kernel to pass data from one process to another. And you also need to modify exec function to redirect file descriptor 0 of the child. And you have to synchronize read and write system calls on a pipe file. So here are our files you need to modify, and you can also feel free to modify the other kernel source and headers. So here is a background knowledge about why the pipe is necessary. The Unix-like system separates the fork function and exec function. Fork function creates a child process and make that process ready to run certain user program. And exec function actually makes the child process to start certain user program. The reason behind the design that separates fork and exec function is to enable the user to manipulate various settings just before executing a new program, and to make the I/O redirection and pipe possible. So for example, we can make the content of certain file as an input of another user program. And by using the pipe, we can make an output of certain command as an input of another user program. For example, echo hello world pipe wc, we can make the output of echo hello world as an input of the following wc command. So the pipe is the heart of the shell programming. So dupe system call duplicates the file descriptor. An argument of dupe system call is the file descriptor that will be duplicated. Dupe system call finds an empty slot from the beginning of the file descriptor table. And if it finds an empty slot, it duplicates the target file descriptor entry to the empty slot. A pipe is a kernel buffer that is used for communication between two processes. And the argument of pipe system call is an array that consists of the two entries, and each entry of the argument array contains the file descriptor. So when the pipe system call completes, the first entry of argument array contains the file descriptor of the read end of the pipe, and the second entry of the argument array contains the file descriptor of write end of the pipe. So this slide shows an example of using pipe. So assume that we run a command echo hello world pipe wc, and the parent process runs the echo hello world and creates the child process, and child process will run wc command, and the parent process pass an output of echo hello world to the input of the child process by using a pipe. So the actual code of this command is shown in the gray box on left bottom. So the parent process runs the pipe system call, and the operating system creates the kernel buffer for pipe, and pipe system call makes the file descriptor 3 of the parent process to point to the read end of the kernel buffer for pipe, and make the file descriptor 4 to point to the write end of the kernel buffer of pipe. And then the parent process runs the fork system call, and fork system call creates the child process, and the child process inherits the parent process state and parent process file descriptor table. So the file descriptor 3 and 4 of the child process are pointing to the read end of the write end of the pipe, respectively. And the child process runs a set of code, the close 0, dupe p0, close p0, and close p1. And this set of codes is for redirecting the standard in of child process to the read end of the pipe. So for example, the close 0 code close the existing standard in of the child process, and the child process runs the dupe p0, and this close the file descriptor 3 that is pointing to the read end of the pipe in the child process, and the close p1 makes the child process to close the file descriptor 4 that is pointing to the right end of the pipe. And so at the end, the child process, the standard in is pointing to the read end of the pipe. So, and then the child process runs the exact function. So it runs the wc command, and it takes the input of the wc command as the read end of the pipe. At the same time, the parent process runs close p0, write p1, and hello world and close P1. And this code is for transferring the hello world string to the child process via the pipe. So by running the close P0, the parent process shut down the read end of the pipe, and it writes the hello world string to the P1, which is pointing to the right end of the pipe, so that the child process can read the hello world string from the pipe. So unfortunately, the Pintos is not same with the Unix-like system. The Pintos does not have the fork function. Pintos only supports exec function. So exec function in Pintos is equivalent to fork function and exec function in Unix, since the exec function in Pintos creates the child process and make the child process run the user program. So here is a problem. A pipe example without fork. So in Unix, the child process comes back to user space and calls system calls before exec function to redirect the standard in to pipe file descriptor, but it is not possible in Pintos, since the child cannot come back to user space. So the solution is modifying exec function. So we will not call def system call to redirect standard in of the child. Instead, we modify exec function to copy and manipulate file descriptor table of the child. So you have to modify exec function to work as a combination of fork function, def function, and exec function. And instead of the def function, the exec function should detect pipe file descriptors and replace standard IO with pipe file descriptors. So here is the detail of solution. So when you run the pipe in Pintos, the Pintos code should allocate the resource related to the pipe. For example, the pipe buffer in the corner area. And the file descriptor should point to the read and the right end of the pipe. And when the Pintos runs the exec function, it creates the child process. And since the child process inherits the state of parent process, the file descriptor table of child process should be same with the file descriptor table of parent process. And what you have to care is to make your exec function to automatically detect whether there is a file descriptor related to the pipe files. So if there is a file descriptor related to the pipe, you have to make sure to redirect the standard in of the child to point to the read end of the pipe, and original pipe file descriptors of the child should be reclaimed. And as I said before, your exec function should automatically detect whether the file descriptor is related to the pipe file. And to implement this, we highly recommend you to declare a new file fd type, for example called fd pipe read and fd pipe write. And for each file descriptor, you can set the associate the fd type, and by using this fd type you can detect whether file descriptor is related to pipe or not. So here is an example of using the fd type to detect the pipe file. So in the figure, the parent process has the file descriptor 4 that is pointing to the right end of the pipe. So you can set the type of the file descriptor 4 to fd pipe write, and the child process has the file descriptor 0 that is pointing to the read end of the pipe. So you can set the file descriptor 0 type to fd pipe read. So here is a requirement for the pipe system call. You have to allocate a small ring buffer in the kernel space that will be used as a buffer for the pipe. And you also need to find the two unoccupied file descriptor that will be used for read end and the write end of the pipe buffer. And return the pipe system call returns 0 if the caller succeeds above 2 tasks or -1 otherwise. Here is a system call semantics for write system call. Your write system call should consider the pipe file. That is, if a process attempts to write to the read end of the pipe, the system call should return -1. Here is another case you have to consider. Assume that one process is writing on the certain pipe, but there is no process that is reading from that pipe. Then in this case, this case means that all pipe read file descriptors are closed. So in this case, the write system call on the pipe should return -1. Here is a normal scenario of using the pipe for communication between two processes. So the process in the left side is writing the string operating enter to the pipe buffer. So first of all, the writer process acquired the log related to the pipe. And then the writer process write the strings, the operating on the pipe buffer. And then the pipe buffer becomes full. So in a view of writer process, there is no space left to write the remaining characters onto the pipe buffer. So it releases the lock related to the pipe buffer, and the child process starts reading the characters from the pipe buffer. So it acquires the lock of the pipe, and it starts reading the characters in the pipe buffer. So the child process holds the lock of the pipe, and it reads the character in the kernel buffer one by one. So in this case, the child process reads the two characters from the buffer. So the read end moves by 2 characters in this case. And the read system code that reads 2 characters returns. So the child process releases the lock of the pipe, and then the write process acquires the pipe file and write the remaining characters G and enter to the pipe buffer. So when the write process finishes writing all the characters to the pipe buffer, the corresponding write system call returns successfully. So your write system call should consider the pipe file case, and here is a requirement. So if the file descriptor fd represents the right ends of the pipe, the contents in buffer should be written on the pipe buffer as if the pipe is a file on disk. And if fd represents a reader's end of a pipe, this should return -1. And if all readers close the pipe file descriptors, the system call should return -1. If the buffer becomes full, the writer should wait until the reader consumes the contents in the buffer. And it does not return until side bytes are written on the buffer. And here is a system call semantics for the read system call. You have to implement your read system call considering the pipe file case. So if the process attempts to read from the descriptor that is pointing to the right end of the pipe buffer, your read system call should return -1. When one process is reading the pipe buffer, there can be no more writer process of that pipe buffer. In this case, the read system call of the pipe buffer does not return error. That read system call just read the bytes left in the ring buffer. So this is not an error case in read system call, unlike the write system call case. So record that the error case of the write system call. So when the writer process is writing on the pipe buffer, but there is no more the reader process of that pipe buffer, then write system call should return -1, as I told you before. So this is because there will be no thread to read the pipe buffer, so the write system call without readers has no meaning. Otherwise, the reading the pipe buffer without any writer does not return error. So here is a normal scenario of read system call on the pipe buffer. So assume that the reader first acquires the log and semaphore of the pipe file before the writer write on the pipe buffer. So in this case, there is no letters written in the pipe buffer, so the reader process does not have any data that the process can read. So the read system call just return the 0 since it does not read any letters, and the reader process releases the log related to the pipe buffer. So after the reader process releases the log of the pipe, the writer process acquires the log of the pipe and it writes the contents to the pipe buffer. So when the pipe buffer becomes full by the writer thread, the writer thread releases the log of the pipe and the reader reacquires the log of the pipe, and the reader process reads the contents from the pipe buffer. After reading all the contents of the read system call from the pipe buffer, the read system call returns successfully, and the reader process releases the log of the pipe. And this cycle repeats until the reader process reads all the contents in the pipe buffer from the writer thread. So let me skip the remaining slides since the contents are the process is same. So here is the summary of the read system call requirement related to pipe file. So your read system call, if the FD file descriptor represents a reader's end of a pipe, the contents in pipe buffer should be written on buffer as if the pipe is a file on disk. If FD represents a writer's end of a file, your read system call should return -1. And this system call consists of two steps. First is waiting for completion of data production if there is nothing to read and the writer's end is not closed. And second is copying the minimum bytes from the pipe buffer to buffer. And your read system call returns the number of bytes read if it succeeds. You also need to implement the close system call considering the pipe. So when all file descriptors of the pipe are closed, the pipe buffer should be deallocated and reclaimed. So to check whether you have implemented the pipe well, please run make check command. We provide 6 test case and no hidden test case. Note that do not run the make grade but run make check. So we provide 86 test case in total. So for 80 non-pipe test case, you can run make grade command, and for 6 pipe test cases, you can use the make check command. So here is a grading policy. And thank you for giving attention and good luck. Thank you.